In this video, we're going to lay out some ideas about how the quantum mechanical model of the atom, which is the current one that we have, attempts to explain where the electrons are in atoms. To start out with, we have to recognize that there were some failures of the Bohr model of the atom. So it seemed like really genius. It followed all the laws of physics, and he was able to come up with this model that explained the line spectra and used physics that everybody understood and accepted. But there were a couple of problems. As they tried to expand this for more complicated atoms than atoms that had just one electron, it just never really worked. And the smartest brains in the world were working on this, and they just could never figure out why this wouldn't work for atoms that had more than one electron. And an even deeper problem that led them to kind of abandon the search was something called Heisenberg's uncertainty principle. So Werner Heisenberg, whose picture is shown here, came up with the idea that there were limitations on how much you could know about two properties of the electron. There's this very interesting video from 3 Blue 1 Brown that kind of explains the general idea of uncertainty, but let's narrow in on the part that's relevant to us. The position and the momentum of an electron are two things that fit into this uncertainty principle model, where you can't know one of them with great certainty without not knowing the other one with great certainty. So that means if you're fairly sure about the position of the electron, then you're not so sure about where it's going. In other words, what its momentum is, what its current velocity is. But if you're very sure about where it's going, its momentum, then you're not going to be very sure about its position. So there's this kind of a trade-off. And Bohr was saying, now you know both. You know what orbit it is, you know how big that orbit is, and you know this energy that it has, in other words, the momentum that it has in that orbit. And the uncertainty principle says that you can't do that. Here's a little bit maybe easier to understand graphic that tries to get at explaining this. You can see that as the red arrow that explains the momentum, or the velocity, where the thing is going, becomes more certain, it becomes like one solid arrow. The where it is, that's the blue dot, becomes really fuzzy. You don't really know. And vice versa. When the blue dot becomes very solid and certain, the momentum arrows are like all over the place. It splits up into lots of different possibilities. That was the idea of Heisenberg's uncertainty principle. Now, this is general, kind of hand-wavy, not very precise statement of the uncertainty principle. And if you take a quantum mechanics class in college, you will learn this much better. But I think this is a way for us to sort of wrap our brain around what the uncertainty principle is and why Bohr's model, which is saying you do know the momentum and the position at the same time, couldn't match this once Heisenberg's uncertainty principle became understood. So the next person who made an advancement was Erwin Schrödinger. And Erwin Schrödinger came up with this idea of quantum mechanics by beginning from the idea that electrons are a matter wave. So he wasn't thinking about electrons as a particle. He was thinking about electrons as a wave and just working with that. And this is very complicated. Most of you will probably never have an opportunity to study it in depth unless you go into very specific majors in college. But we can get a sort of a hint at it by looking at very simple waves and then sort of expanding from there. So imagine you have a single-dimensional, one-dimensional string wave, and it's fixed on both ends. So this is what was called a standing wave. One mode that this string could vibrate in is one in which you have a half a wavelength across the whole length of the string between the two fixed ends of the string. So imagine this would be like a piano wire or a guitar string or a violin string. It could oscillate back and forth in this way. And the wavelength would be twice as long as what we see here, twice as long as the string. And so that's what lambda is. Lambda is 2L because the string is a half of a wavelength. Another mode of vibration that you could have is where one wavelength just fits into the length of the string. So the ends are fixed. You notice that they're not drifting up and down like if you had a piano wire or a guitar string, they would be fixed on both ends. But it could vibrate in this way in which one wavelength is the length of the string. The next mode of vibration that you could have is where there's 1.5 wavelengths in the length of the string. So in this case, the wavelength is going to make up 2/3 of the string. And you can see that there's a node about here, and there's a node about here. Those are places where the wave never deviates from 0. And the other nodes are present, where it's fixed on the ends. And here there's a single node right in the center that the wave never deviates from 0 there either. So, from the end of the string to this node, that's a wavelength. So that's 2/3 of the length of the string is one wavelength. And then the next mode of vibration you could have is where 2 wavelengths fit on the length of the string, and now you got 3 nodes in the middle and then your 2 on the end. So lambda is half of the wavelength. And without breaking the string free from the ends, there are no other allowable modes of vibration, unless you just have more waves in the length of that string. So this sequence could keep going up basically to infinity. But in between these, there are no modes of vibration that could possibly happen with a standing wave. So that means there are only certain allowable wavelengths, and you could describe them with this equation. You could say lambda is equal to 2L divided by N. So where L is the length of the string, lambda is the wavelength, N is a number that can be 1, like in the first one, 2L over 1 is 2L, or it could be 2 in the second one, 2L over 2 is L, or it could be 3 in the third one, 2L over 3 is 2/3 L, or it could be 4 in the fourth one, or it could be 5, 6, 7, 8, but it has to be a number that starts at 1 and goes up by whole numbers. So this is the wave function for a one-dimensional wave. Okay, so there's an equation that will describe it, but you need this number, this quantum number, n, that tells you what are the allowable wavelengths. Erwin Schrödinger recognizes that an electron wave, a matter wave, is going to be a 3-dimensional wave. And like our one-dimensional wave required 1 quantum number, n, 3-dimensional waves are going to require 3 quantum numbers. Another thing that makes this very hard to do is that the math of a 3-dimensional wave is going to be quite complicated. So what Erwin Schrödinger comes up with is he makes the same equation that Bohr did, kinetic energy plus positional energy is equal to total energy, but he does it for a wave, and he does it for a 3-dimensional wave. So what he comes up with is this equation. This is an example of something called a differential equation. So the equations that you work with in the algebra classes and pre-calc, things that you have taken now, if you solve the equation, the solution is a number, or maybe sometimes it's a few numbers, like in a quadratic equation. In a differential equation, the solution to the equation is an equation. It's a function. And the function here, in this case, is given by psi, this Greek letter psi. And you can see that this is a function of psi, this differential equation. It's a function of a function. So this term here, that's your kinetic energy term. This term here, that's your positional energy term, and that's your total energy term. So it's an energy summation. If you're in calculus, you probably have seen something like dy dx at this point as a notation for differentiation, like the change in y with respect to x. That's what these are too, except for these are the second derivatives. So you may have seen d2y dx squared maybe as a notation for the second derivative. These are second derivatives, but it's a 3-dimensional wave, so you have to do it in x-axis, y-axis, and z-axis. So those little Greek deltas, those things there, those are the d's, but they're partial derivatives. They're derivative in that axis, so you have to have 3 of them. Okay, so if you don't understand any of that I just said, that is perfectly fine. But suffice it to say that smart people like Schrodinger, who were very well educated and knew a lot of math, could solve equations like this. But to do them required that you specified 3 quantum numbers, and those quantum numbers had to fit into certain rules, just like our one quantum number had to fit in rules to match our one-dimensional wave. So if none of this Schrodinger equation makes any sense to you, you're not alone. I'm sure your classmates mostly feel that way too. But we are going to try to make a little bit of sense out of this, and I think it is possible to do that. So here are the quantum numbers. This part is important for us, and we'll get some interpretation for this later on. One of the 3 quantum numbers that's needed is a number that we call n. This is called the principal quantum number. That's the name of this thing. It has this range, the same range that the string waves did, the same range that Bohr and Rydberg had in their work as well. And it starts at 1 and it goes up to infinity, but it's only whole numbers. The next quantum number, sometimes called the secondary quantum number, it's sometimes called the angular momentum quantum number, sometimes it's called the orbital quantum number. This has a very similar range, but it starts at 0, not at 1, and it stops not at infinity, but it stops at 1 less than whatever n is. So for a wave function that has n equals 1, for example, the only possible value of L would be 0, because it has to stop at 1 less than 1. If the principal quantum number, the n, was 2, then L could be 0 or 1. If it was 3, L could be 0, 1, or 2, and so on. The next quantum number is called m sub L, or this is called the magnetic quantum number. And this can have negative values, and its range is negative L to positive L. So if L is 0, then it can only be 0. M sub L can only be 0. If L is 1, then it can range from negative 1 to positive 1, but through integers. And so that would be negative 1, 0, and positive 1. If L is 2, M sub L could be negative 2, negative 1, 0, positive 1, positive 2. So M sub L is limited on both sides, but it can be negative. And once again, it's only whole numbers. All right, here are some solutions for the hydrogen atom wave function. So here's n in the first column. N could be 1. If n is 1, the only possibility for L is 0. And if the only possibility for L is 0, the only possibility for M sub L is 0 as well. So that means there's only one solution for the n equals 1 quantum number. There's only one set of quantum numbers, and that's 1, 0, 0. So here's psi 1, 0, 0. That means that's the designation of which quantum numbers you're using to find your solution, and that's the equation that is the solution to Schrodinger's equation. Now, don't worry about what it means at this point. It's complicated, I admit. So just don't worry about it. Forget about it. But look at this. When n is 2, L could be 0, and then M could only be 0. So psi 2, 0, 0, that's another solution. Now when L equals 1, M could be 0, or it could be minus 1, or it could be plus 1. So now we have psi 2, 1, 0, that's one solution. And then we have 2 solutions for if M sub L is negative 1 or positive 1. So here are 2 solutions built into one. The only difference is E is raised to either the plus or the minus of those symbols, right? So don't worry about what that means at this point. We'll come back and try and get a little bit of meaning for that later. If n equals 3, then L could be 0, and M could be only 0 again. L could be 1, so M could be 0 or plus or minus 1. If L is 2, then you have a bigger range, and it's not all shown in this chart, but M sub L could be 0. It could be plus 1, minus 1. It could be plus 2, minus 2. So there'd be a bunch of solutions that would be possible there. Psi is a function that describes a matter wave, a 3-dimensional matter wave. And there is a small group of people in real esoteric fields that work in physics departments in universities who will think about electrons as matter waves. And they have a deep understanding of these mathematical models. For us, as chemists who are trying to figure out how can we use the properties of electrons in atoms to predict how chemical change is going to take place. It's much more useful for us to have a particle interpretation of psi. And in fact, it turns out that there is. If you square psi, or do an operation that's very much like squaring psi, that wave function, you can get a result, a function that describes the probability of finding the electron if you think about the electron as a particle at any location. And it's important to think about this as a probability because remember, Heisenberg's uncertainty principle makes it clear that we can't know where the electron is and where it's going at the same time. The only thing that we can do is pin down where it is likely to be if we could nail down its location. So it's a probability thing. Now psi is a function with 3 quantum numbers because an electron is a 3-dimensional wave. So you need to work in 3-dimensional space. And X, Y, and Z turn out not to be the most convenient ways of setting up your coordinate system in 3-dimensional space when your atom is considered to be spherical. So we're going to use R, theta, and phi, and let's lay out the space. This is what it's look like. R is how far the electron is from the nucleus, the radius. Phi, if you think about a flat plane, like the X and the Y in an XYZ coordinate system, phi is how far around that 360-degree circle or 2 pi radian circle is the electron located. So think about this radius as being able to sweep around in that flat plane, and how far it has swept around, well, that would be measured by phi. And then the third coordinate in our coordinate axis system is theta, and you can think about theta as being how far above that flat circle the electron here, that blue dot, can be located anywhere in 3-dimensional space by specifying a radius, how far away it is, a phi, how far around the 360-degree circle on the bottom is it, and then theta, how far in the 360-degree circle that is the YZ or XZ plane is it. Now let's go back to those functions. Here we can learn a little bit of something. They use the letter rho here instead of R. But look at the solution for when n is 1, L is 0, and m sub L equals 0. Psi 1, 0, 0 is 1, a constant, divided by the square root of pi, which is a constant, times z, which is a constant, that's just the charge in the nucleus, divided by a naught, another constant, raised to 3 over 2, that's a constant, times e raised to the negative rho. So the only thing that isn't a constant in this whole thing is rho, or the radius. So this only depends on the radius. The probability of finding the electron is only going to depend on the radius. So that means it's spherical. It doesn't matter how far around you are in either of those two angular dimensions. It only matters how far away you are from the nucleus. So this is a sphere. When n is 2, L is 0, m sub L is 0, then look at psi 0, 2, 0, 0. Constant, divided by a constant, 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 constant. 2 minus, there's rho again, e raised to the negative rho over 2. Again, the only thing in here that isn't a constant is rho. So when m sub L is 0, even if n is 2, again, it only depends on the radius, which means it's spherical. If you look down here at n equals 3, L equals 0, m sub L equals 0, look at the function. Constants, constant, constant, constant. There's rho, and there's rho again. But phi is not in there, and theta is not in there. So again, it's spherical. Okay, now let's look at when L equals 1 and m equals 0. So look at this function. Constant, 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 constant. There's R, E, there's R again. Now theta shows up. So now, not only does it depend on how far you are from the nucleus, but it also depends on how high up above the kind of XY plane are you. So that's going to matter. It's going to not be spherical anymore. Look at when m sub L is either plus 1 or minus 1. Looking at all this stuff here, there's r, there's theta, and there's phi. So now it depends not only on how far above the xy plane are you, what angle above the xy plane, and the radius, but now it also depends on how far around in that xy plane are you. So this is truly varying in all three dimensions. And when n equals 3, L equals 1, m equals 0, again, it's all constants except for rho and theta, so it only depends on the radius and how far above the xy plane you are. And then when L is either plus or minus 1, we're back to it depending on r, theta, and phi, all three dimensions. Now it gets really complicated after that. It's already complicated enough. So let's just drop that for now and then move on to learn some more things about an interpretation of this. The idea that this is a probability led people to come up with the concept of an orbital. Now, an orbital is not an orbit, even though the word orbit is in it. An orbit is like a specific pathway for the electron. This is different. An orbital is a region in space that is associated with each one of these wave functions, each one of these psi's, that is centered on the nucleus and encloses a zone where the probability of finding the electron is high. In fact, the cutoff that they use is 90%. So a region in space, just a zone in space, inside of which the electron will be found 90% of the time, is what we call an orbital. So an orbital is not a thing. An orbital is just a zone in space where electrons are likely to be found. Now here are the interpretations of the three quantum numbers as they relate to orbitals. The principal quantum number n, this relates to the size of the orbital. In other words, how far the electron in that orbital is from the nucleus on average. So the bigger n is, the bigger the orbital is, and the farther away the electron is going to be most of the time from the nucleus. In some other terminology, this is also called the electron's shell. So here are the examples for when L is 0, which means m sub L is 0, for the first three quantum numbers, 1, 2, and 3. They're spherical, as we already saw, because they only depend on radius. When n is 1, it's a pretty small sphere. When n is 2, it's a bigger sphere. When n equals 3, it's an even bigger sphere. Here's an interesting kind of little sideline. If you make a graph of the probability, let's just call that probability of where the electron is, and the radius, r, or rho, for n equals 1, you get a shape that looks like that. And that region right there, that spot, that's the highest probability of finding an electron. And in fact, that corresponds really precisely to what Bohr figured out for his orbit radius for n equals 1. Now, Bohr's mistake was that he assumed that the electron was always in that orbit, and the reason it made sense was because the electron is most likely to be in about that area. And then for n equals 2, well, it's going to look kind of like this. The highest probability of finding an electron is farther away from the nucleus, and then there's this little region in here where it drops down. This is a very good drawing. It drops down almost to 0. That's a node in the middle. So there's a high region of probability. You can find it there, and then another high region of probability. You can find it out there. But then in the very middle, and then in between those two kind of zones, there's a node. And for n equals 3, well, there's 3 of those. You can see those 3 nodes, but it stretches out, farther in radius. The value of the orbital quantum number relates to the shape of the orbital. So there's this pattern, whatever L is, like we saw when L is 0, that means a spherical orbital. It kind of dictates what the shape of the orbitals are going to be. This also is called the electron's subshell, whatever the value of L is. So here's how the shape thing works out. When L equals 0, as we've already seen, that's spherical. That's called an S subshell. We give it a little shorthand. And part of the reason for this shorthand is because we want to be able to distinguish which quantum number we're talking about. So if we said, like, it's 1, 0 or 1, 1 or 2, 1 or 2, 2, you wouldn't know which quantum number necessarily goes with what. So instead of saying L equals 0, we just say S. So we would say when n is 1, and L equals 0, we would call that the 1s subshell, for example. When L is 1, we call that the p subshell, and the shapes of these orbitals are kind of dumbbell shapes. So remember, one of those probabilities depended only on radius and theta. That's this one in the middle. You can see that it's, the farther you are up from this axis, or the farther you are around that axis, the probability is going to change, and also it's going to change with the radius. These two depend on theta and phi, so those are the other two. That's the +1, -1 version. When L equals 2, that's called a D subshell, and these have 4 lobes, like 4 regions that make up that orbital, there and there and there and there. And this one's a little bit different than the others. And when L equals 3, that's what's called a F subshell, and these are very complicated. They have 6 regions, typically, of electron, like zones where electrons are likely to be found that make up that single orbital. And then, again, there's one in the middle that's just a little bit different than the others. So then the final quantum number, which is the magnetic quantum number, m sub L, this relates to a specific orbital in a subshell. So there's a kind of an organization to where the electrons are in an atom. One way of thinking about this is almost like an address, or maybe an even better interpretation of a sports event at a stadium. So groups of orbitals make up a subshell, groups of subshells make up a shell, and groups of shells make up an atom. And remember, none of these things are actual things. They are just descriptions of regions in space where electrons are likely to be found. All of the quantum numbers that we have so far are descriptions of orbitals that arise from those wave functions that were solutions to Schrodinger's equation. But it turns out that there's another quantum number that relates to a property of the electron itself. So it was determined that this fourth quantum number existed, called the spin quantum number, m sub s. And the spin quantum number arises from the idea that electrons are charged particles and are spinning around. And that means a magnetic field. They develop a magnetic field. And it turns out that they only really are spinning in 2 different directions. So that if you put them in an external magnetic field, some of them are going to spin in a way that as they pass through the magnetic field, they're going to move upwards. And some of them are going to spin in such a way that as they pass through the magnetic field, they're going to move downwards. So here's a sort of a picture of a kind of a representation of that. The ones that are spinning in the one direction in that magnetic field are called spin-up electrons, and the other ones are called spin-down electrons. And there are 2 different numbers that we have for spin quantum number, because there's only 2 directions. There's a up and a down. One is -1/2, and the other one is +1/2. And I don't even remember why they're called 1/2, +1/2, and -1/2. If you take a quantum mechanics class sometime, you might find that out. But there are just 2 of them, and that's really the key thing. There are just 2 directions of spin, and so there's 2 quantum numbers. The important consequence of that is valuable for us is that it was found out later on by this guy, Wolfgang Pauli, that no 2 electrons in the same atom can have all the same quantum numbers, the same 4 quantum numbers. So since n determines the shell, L determines the subshell, m sub L determines the orbital, and there's only 2 values of m sub s, +1/2 and -1/2, that means the maximum population of any orbital can only be 2. Because if you have, let's say, n equals 1, L equals 0, m sub L equals 0, that's an orbital. M sub s could be -1/2, it could also be +1/2, but it couldn't have any other value. So the maximum population of any orbital is 2 electrons. All right, now let's get to something practical that we can do with these ideas of orbitals and of quantum numbers. There is this principle called the Aufbau principle, which literally means building up in German. And the principle states that electrons in the ground state atom, in an atom that doesn't have any extra energy having excited it, are going to occupy the lowest energy levels that they possibly can. Now here's a way of interpreting what that means. Imagine that we have a graph where we have energy on the vertical axis, and there really isn't a horizontal axis, there's just different levels. Remember, the atom is quantized. That's one thing that the quantum mechanical atom and Bohr's atom have in common, that there are these certain values that can exist for energies of the electron and some that can't exist, so it's quantized. When n equals 1, then the only possible value of L is 0, so that means there's only one sub-level or subshell, and that's the 1s subshell. So this is for when L equals 0. If L equals 0, then the only possible value for m sub L is also 0, so that means there's only one possible orbital. So the 1f sublevel has one orbital. I'm going to represent an orbital as this set of brackets. 2 electrons could fit in there. So for hydrogen, for example, it only has 1 electron. It's going to fit in that orbital because that's the lowest energy level. That's where it's going to be. And if it's helium, helium has 2 electrons in a neutral atom. And so that means those 2 electrons are going to fit in that orbital as well. But if you go to lithium, which has 3 electrons in the ground state, those things cannot all exist in that orbital because there's only room for 2. And we can think about spin up and spin down almost by drawing arrows that point up and down. So if this is like helium, for example, that's where the electrons would be. Both electrons would be in that single orbital in the 1s. But if you move to lithium, well, now we have to have another space for that additional electron. So we have to move up to level 2. So if n equals 2, well, now L can have 2 values. L could be 0, but it could also be 1. So that means there's 2 subshells. One of them is the 2s. That's where L equals 0, which again means m sub L can only be equal to 0, so there's only one orbital. So that third electron from lithium would go in that orbital. And then if we moved up to beryllium, that's going to have 4 electrons. There's room for that 4th electron to be in that orbital. That would be spin down because they have to have opposite spins, or they'd have the same quantum numbers. Okay, now let's say we move up to boron, which has 5 electrons. There's not room in those 2 subshells anymore, so we have to move up to the 2p. 2p happens when L equals 1. And if L equals 1, then m sub L could be -1, 0, or +1, because it can range from -L up to +L, which means there are 3 orbitals in that subshell. So for boron, that electron is going to go in there. Then let's say we go up to carbon. Where's that electron going to go? Well, there's room for up to 6 electrons in here. It turns out that it's going to move to an open orbital. Electrons don't like to pair up within an orbital unless they have to. There's a principle that we're going to get to in a bit. Okay, so if we go to the next one, nitrogen, we have to have an additional electron in there. And then oxygen, 1 more electron. There's still room, but we have to start doubling up now. And then fluorine, have to double up in another orbital. And then we finally get to neon. Now we double up in that 3rd orbital in the 2p subshell. But now there's no more room for electrons. So if we start the next row, which is going to be sodium, Na, we have to have room for 11 electrons. So we need more shells. So now we move up to n equals 3. If n equals 3, L can be 1 or 0 or 2. So that means there's 3 subshells. We've already seen that the 3s has 1 orbital and the 3p is going to have 3 orbitals, but D is the subshell where L equals 2. So that means m sub L can range from -2 through -1, 0, +1, +2, which means there's 5 possible orbitals. So now we have room to place 10 electrons in the D subshell, 6 electrons in the P subshell, 2 electrons in the S subshell. So now we could get all the way up to quite a few electrons. Now as we continue to add more shells, there continue to be more subshells per shell, and things start to get really crowded. And so this is probably a pretty good place to stop this energy diagram and move to another way of thinking about the alpha principle in atoms. So on the periodic table, there are some patterns here. And when these interpretations of the orbitals and the shells and the subshells started to come out, chemists latched onto this right away because they looked at their periodic table and they're like, we already have these patterns. they accepted this as a very reasonable model for the atom because it fits stuff that was already present on the periodic table that already existed. Now the periodic table is arranged by properties of materials. So like all the things in this column here have very similar properties. And that's why they ended up in that column. Before anybody knew anything about the quantum mechanical model of the atom, this periodic table is arranged the way it was, with most of these elements probably already in place at that point in time. And they recognized that they had a group of 2. That's like an S subshell, 2 electrons. They had a group of 6. That's like a P subshell, 3 orbitals, 6 electrons. Here's a grouping of 10. 5 orbitals, 10 electrons. These down here, those are groupings of 7 orbitals, 14 electrons, 14 elements. And as you fill the electrons in, you're going to fill in 7 orbitals. So there's a shortcut that we can take right off the periodic table as we do the Aufbau principle. The principal quantum number is going to be the period that you're in, the row number. So n equals 1, that's the first row. And this is a little bit of an exception because helium is over here, hydrogen's over here, but this is 1s. That's the first 1s electron. That's the second 1s electron. 2s, 1, the second 2s electron. This is the first 2p electron. The second 2p, the third 2p, the fourth 2p, and so on. Then when you get to the blue ones here in the middle, these are the Ds, that's actually the period number minus 1. So if you're in the fourth period here, as you go through these elements, you're filling the third D subshell. And the Fs are 2 minus the period number. So these actually go there and there. So in row 6, period 6, it's going to be 6s. This would be 5d. This would be 6p. But this is going to be 4f down here that goes in the middle. Now the reason that these are placed down here is just because it fits on a rectangular piece of paper better. They really belong in between there and there, but that would just make this really wide and short. Okay, so let's do something practical with this. One of the ways to describe the electrons in atoms is with something called electron configuration notation. So in electron configuration notation, you list all the occupied subshells, any subshell that has an electron in it, in Aufbau order. In other words, from lowest energy to highest energy. You show the population of electrons in each subshell by superscripting that population up to the right. So let's do some examples. What's the electron configuration notation for the first 11? Let's start out with hydrogen. Its single electron is in period 1, subshell S. So we would say 1s1. Helium. Now you're through the 1s1 and you're to the 1s2. So helium is 1s2. Lithium. Now we're through the first row. So for lithium, we're going to start out with 1s2. That's full as we go through that row. And then you have to use the 2s subshell for that third electron. Beryllium, now you have to fill the whole 2s subshell. So beryllium would be 1s2, 2s2. Boron, now we've completely filled the 2s and we're into 2p. One step into the 2p. So that fifth electron is going to be a 2p electron. So for boron, 1s2, 2s2, 2p, 1. Carbon, we're just extending one more into this p block. There's room for 6, remember. So we're going to keep going. Carbon is 1s2, 2s2, 2p2. Nitrogen, one more step over. So nitrogen's 1s2, 2s2, 2p3. Oxygen, you're one more step over. 1s2, 2s2, 2p4. Fluorine, keep going. 1s2, 2s2, 2p5. That puts you there. And then neon, 1s2, 2s2, 2p6. You came to the end of the row. That means you've filled all the subshells in row 2. Now we're starting over. Go up to 11. This is our last one that we have to do. Neon, 1s2, 2s2, 2p6. That gets us all the way through the second period, and then we're starting the third period with 3s, population 1. And if we add the electrons up, 1 and 6 is 7, and 2 is 9, and 2 is 11. That's the number of electrons in neon. And then you can just keep up with this pattern. So let's just grab a random one a little bit farther down. Let's do selenium, just for practice. Selenium's number 34. Let me get rid of all this stuff. We're going to do selenium. We're doing electron configuration for number 34. So on our way to 34, we're going to go through period 1, which is 1s, 1 and 2. Then period 2, 2s2, 2p6. Then period 3, 3s2, 3p6. Then period 4, which starts out with 4s2. And then it goes to 3d, because remember the d's are 1 less than the row number. 3d all the way to 10. And then back up to 4, because p's are the same as the row number. 4p, 1, 2, 3, 4. So that's how you can just look at the periodic table and kind of trace your way through and write down your electron configuration notation. Another way of describing where the electrons are in atoms that's sometimes more useful, it's also harder to make, is orbital notation. So here you're not only showing the occupied subshells in alpha order, but you're actually modeling each orbital as a set of parentheses, or sometimes people use a box, or sometimes they use a blank. And then you populate those orbitals using up and down arrows to designate the spin. And remember, 2 electrons in the same orbital have to have opposite spins. So let's practice writing orbital notation for the first 11 elements. As we do this, let's keep in mind this thing that I mentioned earlier, that called Hund's rule, that electrons don't share orbitals unless they have to. Let's do this on this slide. So the first element is hydrogen. Hydrogen has 1 electron in the lowest orbital, which is a 1s. So that's what that's going to look like. Helium, we're just going to add an electron. No more room, we have to move to 2s, which is 1 orbital. So for lithium and beryllium, we're going to need this next orbital. So this is lithium, and then beryllium. Okay, now we're through that 2s subshell, so now we need to go to the 2p subshell. Now for a p subshell, or a d, or anything that has multiple orbitals in the same subshell, we're going to write all the orbitals, even if they don't have any electrons in them. So there's 3 orbitals in a p subshell. We'll put 3 sets of parentheses, and then we'll put a line over the top, because they're all in the same subshell. And now we'll start to populate them. So if we're boron's going to have 1 electron in that 2p shell. Carbon, 2. Remember, we're going to spread them out unless we can't. Nitrogen, 3, 2p3. Oxygen, 4. Have to double up now. Fluorine, double up in the next orbital. Neon, double up in the next one. Okay, so now let's do sodium. Sodium, we're done with this row now. Now we have to go to the 3s and stick that 1 electron in there. And if we did magnesium, then it would be like this. And then if we were to go over to start to do aluminum, we'd put that 3p shell in there, subshell, stick that 1 electron in there, and just keep going. So that's orbital notation. Another type of notation that's very helpful is shorthand notation. It turns out that all the chemistry really happens in the highest shell. And so we don't really need to know the details of all the shells below that highest shell. So shorthand notation is very helpful for keeping track of just what's the most important of the electrons for chemistry purposes: aluminum and germanium. Going back to this periodic table to kind of help us out, the first one we're doing is aluminum right there. So what we're going to do is, let's first of all just do aluminum full notation. 1s2, 2s2, 2p6. That gets us through the second period. And then now we're in the third period, which is aluminum's period. 3s2, 3p1. So that's the electron configuration notation for aluminum. What we're going to do is we're going to take 1s2, 2s2, 2p6, which is the electron configuration of neon, and we're just going to replace that all with neon in square brackets. And then we're just going to put the rest of it. So we go to neon, and then we start actually putting in our electron configuration notation. So we're at 3s, 1 and 2, and then 3p1. So that's shorthand notation. You're just writing down the previous noble gas in square brackets and then finishing the important part of the electron configuration notation for chemistry purposes. Now let's do germanium next. So you go up and over to the right. We say that argon is the previous noble gas. So for germanium, we're going to start out with argon in square brackets. That's period 3. So then we're going to start our actual notation at period 4. We're going to go through the 4 S's first, 4s2, then the 3 Ds, all 10 of them, and then 4p, 2 spaces. That 3D, that should be a 10. My pen didn't pick that up. And you can do that also with orbital notation. So for example, if we wanted to do orbital notation for aluminum, we could do neon, and then we'd have our 3s orbital, and then we'd have our 3p orbitals with 1 electron in it. So you can use shorthand notation that way too. I know this is really complicated stuff, and it seems like a lot to keep track of, but the things that we've been doing in the last few slides, where we're doing orbital notation and electron configuration notation and shorthand notation, those are actually the most important parts for the purposes of learning how chemistry works. The rest of that is pretty esoteric physics stuff. But the background helps us understand where these notations come from. If you just memorize these notations, it'll be really hard to remember them or have any sense of their meaning. So it is valuable to delve into that stuff, even if it's mind-bending a little bit.